Okay, so let's restart. I will restart on the corrosion damage and degradation. And for this lecture, I will more focus on basic knowledge of corrosion. So this morning I was mostly giving some description of how we think about corrosion, how we manage corrosion, what kind of corrosion, but we will see more deeply what is corrosion. So we are now in the basic corrosion. So just to refresh, most common materials which we are using in the industries are unstable in air, in the atmosphere. So that was I was explaining this morning. We have to fight with a thermodynamical problem. We can find two exceptions, gold and platinum. So now you know why they are quite expensive. So I already said that we are going back to a thermodynamical state of the materials. And when we deal about corrosion, most of the time, materials, so steels and alloys, will form what we call oxide, passive layer, sulfide layer, and so on. So corrosion is quite complex because there is the thermodynamic, and also we have to fight at the same times with chemical and electrochemical reactions. So electrochemistry means you deal with chemistry and electricity. Because it's thermodynamic, it means that everything depends about the temperature. The problem is life is not only thermodynamics, it's also driven by kinetic. So kinetic means that we have also to take care about time. And there is also the atmosphere. That means that the corrosion rate, the speed of the degradation, will be affected by the environment, meaning that, for example, if I'm focusing in aqueous solution, the ions that I have in solution, the quantity, the high resivity of solution. So that's why you will see that sometimes corrosion happens with some reactions that are reversible, controllable, or not at all. Okay, you are able to stop the reaction by some processes or not at all. Okay. The first parameter on which we are often dealing is the Gibbs free energy. I will try to not show a lot of equation because this is not the equation I'm interested in what we can do with the information. So in thermodynamics and chemical potential, this is also a thermodynamical parameters, we want to reach the equilibrium. In electrochemistry, the spontaneity of the reaction will be, okay, this reaction oxidizes. I will explain later what is the meaning. This reaction reduces. Here, I have listed 3 examples of reaction. So there are oxidation using oxygen, oxidation, oxygen. And if you look for magnesium in water with oxygen inside, you will create a magnesium hydroxide and you have a Gibbs free energy about minus 600 kilojoule. If you look on copper, the Gibbs free energy is only minus 200 kilojoule. If you look on gold, we can have also a reaction of oxidation. In this case, it's plus 65 kilojoule. So that means for some reaction, we have a negative value of Gibbs energy. That means that the reaction that we are looking, for example, the magnesium and copper, they will appear thermodynamically. They have to happen. In the opposite, without applying any stress or any constraint, any load on the system, for gold, we should not have hydroxide on gold. That's the thermodynamic is giving us. This is for the standard Gibbs free energy, so 25 degrees, one atmosphere. So for magnesium and copper, here we just know that it will happen. We don't know how long it will take. Okay, so we don't have any information about kinetics, and I will not really talk about kinetics because it's very, very a difficult problem. Okay, so thermodynamics is not very a useful tool when engineer wants to use it to know if there is corrosion or not. So it has been proposed a couple of 10 years ago, a ratio, what is a peeling bedwork ratio, okay, and this ratio was came from oxidation in high temperature. So this is a case of the two reactions that I gave before, oxygen and temperature. And this ratio actually try to characterize the volume of the oxide that you will create on the volume of the metal. And if you get a ratio below 1, you will have, okay, the consequence of this ratio, sorry, it will be that the oxide film will be too thin. So that means the oxide layer will not be sufficient to protect the material. So you may have a breakdown of your material. So in the case of magnesium, you will see that magnesium will corrode. If this ratio is comprised between 1 and 2, it has been said that, okay, the oxide film may passivating. So here, what we understand by this sentence, it means that you are creating a passive layer that is enough strong. So an oxide layer on your material, which is enough strong, and it will protect the material. If the ratio becomes higher than 2, actually you are creating a lot of oxide. But if you look and if you think about the chemistry of the oxide, this is the material, the iron elements, for example, the metal elements, plus oxygen, plus other things. So it takes a lot of space. And actually, there is problem of steric arrangement of the oxide. So you create what we call chips. And at the end, the oxide layer is not at all compact and dense. So you still not have any protection. This is kind of a first view to characterize in engineering process an oxide layer, and eventually how the oxide layer will behave. There is a lot of limitation. There is some books refer on the slide, so you can have a look on this one. It's yeah. Okay. This morning I said that corrosion actually occurs in different environments, so high temperature, atmospheric, and aqueous. So now I will just come back again a bit with the differences and try to explain a bit what's happening. So high temperature. Still in the community, we still have some discussion about high temperature. Is it 1000 degrees? Is it 200 degrees? Actually, it depends about what kind of process it is considered and the materials that I'm putting in front of the process. So, but the generality is always the same. If we work at low temperature, we will have a slow diffusion of oxygen in the metal, and we will have a compact oxide layer. We have time to reorganize atoms in the interface. So the idea is this small schematic. I have the oxide, the metal, oxygen gas comes to the metal tends to go to the oxide, to the oxygen, and the oxygen goes to the metal, and you create an interface. Actually, this is kind of problem of potential. The environment is at one potential, the metal is at the other potential, and the nature doesn't like straight jump of potential. It tends to softening the jump. So you have to create something which adjusts in any point the difference of potential. This is the oxide. When you increase the temperature, actually, you will still have this diffusion of metals and oxygen in the oxide layer. But as the temperature is higher, energy is higher, so you will have in the same times of the oxide formation what we call oxide volatility. That means that you are losing a part of the oxide that you are creating. So you create and you decreate at the same time. Okay. All these processes are driven by diffusion. You diffuse species through this layer. So diffusion means time. And if you increase temperature, actually, you will generate a very fast oxygen front, and you will have first a diffusion barrier which will be created. You block all the sides of the surface, and after, if the oxygen, if the time is too high, you will have spalling of metals. So just to give you a short draw with some keywords. And if you look on the what's happened in the experimentally on the on the metals, so usually in a high temperature, the first experiment which were done, it was weighting the material. So you have a balance, the material in the balance, you inject the gas, and you follow the evolution of the weight of the sample. Sometimes you can have a decrease, a loss of weight of the samples. So if you decrease the weight of weight, what's happened is you oxide your materials, but the oxide becomes volatile and disappear on the surface of the material. So you decrease. And after, you can also have a weight gain. In this case, the oxide layer is creating on the surface of the material and remain on the surface. It sounds because of oxygen had some weight on your materials. Okay. After, there is some law, parabolic law, linear law, log law, and some laws are sometimes related to the materials that you are looking at. MA is not a material, it's MN. Okay, I will not go too much in deep on that. So high temperature is mostly oxygen. What's happened now when we are in an aqueous environment? So in aqueous environment, we still have water and we still have oxygen. So oxygen will still react with the surface of the material and will create an oxide. Here we have some material exchange. In atmospheric condition, we will have a cycle of dry condition, wet condition. Okay, so during wet condition, we are in this case where the waters cover the surface of the materials, the oxygen in water diffuse and generate an oxide layer. In dry condition, the oxide is drying. eventually chemical elements on the surface because we are in atmospheric condition. For example, you will deposit some sulfide, some polluants. Still, they are in a dry condition, there is no problem, but when water will come again to the surface of the material, the polluant will become dissolved in the solution, becomes ions. If they are ions, they are charged, and electrochemical reaction can happen. Electrochemical reaction means electrons. Ions each charge. Okay. So, which is interesting here, it's to see that not only oxygen and water will act in atmospheric condition, but also other ionic elements, and they can change the nature of the layer that you are creating on the material. And if you are changing the layer here, you will change the properties of resistance against corrosion. Just here to illustrate that if you change the environment, you will change the corrosivity of the corrosivity. For example, here you have the exposure time in years. Here you have the corroded weight. And here it's a countryside atmosphere. If you go to city atmosphere for the same material, you will see that it's increasing. The corrosion of the corrosion rate of the material is increasing. And now, if you are going to industrial environment, you see that the corrosivity is still again increasing. So that means pollutants, not only oxygen, but also chloride, sulfide, and so on, they are increasing the corrosion rate. So I was quite proud because I found a map of Japan, and guys have looked on the effect of the atmosphere on the corrosivity of alloys. So, and in this map there is Sendai, and according to them, the quality of atmosphere in Sendai is something like better than in Tokyo, than Osaka, and so on. Okay, so now if I'm looking in aqueous solution, so now there is not any more drying time and waiting time. It is always wait. So what we have to do? We have to imagine that the metals, the metal which is here, its potential has to be adjusted to the potential of the water. And the water contains ions. In corrosion, it is mostly anions. So minus something. Never, cations are not really important in corrosion. So what we have to do is to adjust the potential. So that means that the ions in solution will be mixed. And if you think about chemistry, first year, there is a law which is called electroneutrality of solutions. So usually we should have ions perfectly distributed in the solution. Because we are also having a surface, a metallic surface, it will change a bit this distribution of ions. Now, corrosion in water, it will occur because of electrons. I already said that a lot. And for that, we need to have two reactions at the same time. The first reaction that will release electrons, and a second reaction that will keep electrons or attract electrons. Okay, if you touch a steel rod in water, it doesn't have any electricity It's electrons already exchanged and stable. So for the case of, for example, of iron, it's quite easy to understand that iron will dissolve. So iron becomes iron 2 plus or iron 3 plus. If they're coming that, they are losing 3 electrons. If they lose 3 electrons, electrons are moving to the electrical conductor. This is the metal. Comes to the surface of the materials, and they are acting with species in the solution, oxygen, and create subspecies. Here it's OH minus, and OH minus will also act for chemical reaction and not electrochemical reaction. Okay. In both cases, no, let's say first in aqueous corrosion, if you understand that dissolve oxygen, so this is the oxygen dissolved in water. If dissolved oxygen is a counterpart of the dissolution of the material, that means that where I have a lot of oxygen available, electrons will be catch, and in the area where there is no more oxygen in the solution, it's mostly the iron which will be dissolved. And here, it's kind of explanation about that. If you put a steel rod, for example, in water, you will see that the corrosion of the steel rod will not appear at the water-air interface, but it will appear below below this interface. It's only because oxygen concentration is located on the surface of the material. Oxygen exchange, they are in atmosphere, they are going to the water, and because they are in the water and there is electrons close, they react, and that's it. It is exactly the same if we look on the atmospheric corrosion. Atmospheric corrosion, actually, this is kind of droplets of water that are homogeneously, more or less, distributed on the surface of your material. In this case, you have an interface between the droplet and the air. Oxygen mostly is concentrated here. It's also diffused slowly in the solution, but because here there is a lot of oxygen available, if corrosion occurs, electrons of iron are released here, electrons move here, and react at the boundary of the droplet, where the oxygen is available. Same thinking if you are looking for pipes in soil, for example. The oxygen concentration is here. This is the top surface. Oxygen diffused to the soil. So there is a gradient of oxygen in the soil. Here, more oxygen than here. So that means here corrosion takes place, and here oxygen consumption of oxygen can happen. Okay. So here that's not very clear, but actually it's a comparison between a pipe upper side and downside with intensity of corrosion, but I have to say that I should choose another picture. It's not so easy to see. Okay. First reaction, I will give sometimes some reaction. The first reaction is, for example, iron in a chloric acid. That's a common experiment that we are doing. If we look, what is the reaction that we will write? Is this one. Okay, this is pure chemistry here. Iron, 2HCl, give this. Okay, now, if we look on the experiment and if we have a more deeper understanding of what's happened, the first point is iron is remain irons. Chloric acid is a very strong acid. So that means it never exists as HCl. It always exists as H plus, Cl minus. I have made a mistake. This one doesn't exist. It's 2Cl minus. And if you have that, and you look what kind of reaction can happen, it's an electrochemical reaction. If I'm watching iron can dissolve, releasing 2 electrons. These 2 electrons can be catched by who? H+. And if you took 2H+, you will get H2, dihydrogen. If you perform this experiment, you will see that there is a lot of bubbling appearing around the steel rod. Okay? So finally, the equation is more something like that. Because chloride remains anions in solution. They will not be attached to iron. They are not stable. So that means in corrosion, we have to have carriers, electrical charge carriers. So we will have negative charge carriers or positive charge carriers. Negative carriers are the electrons, okay, minus, and they are moving in metal. So usually for students, we are saying that electrons does not know how to swim. So that means that if electrons move in the material, the charge may move in water in something, so they are moving in ions. That's the positive charge carrier. Okay, and if there are ions in solution, that means that their mobility, they will depend about the electrical charge, but also the potential gradients, convection, migration, and so on. So there is a lot of parameters. As an example, zinc, it will dissolve in zinc 2+, releasing 2 electrons. Sometimes to help, we are also using the oxidation degree or it is also called the number of oxidation. So here it's given 2+. So as for previously, zinc will dissolve here. So electrons will move. They will move in an area where there is no dissolution of zinc. And what they can find hydrogen, H+, which tends to approach to the surface. H+ wants to take 1 electron. It gives H. So H is adsorbed on the surface of the materials. H attract together at the surface of the materials, and you create H2+. In the example which is given here, H2+ move in the solution. Sometimes H adsorb H doesn't want to go to the solution. They don't want to be associated, and they are going back. They are going inside the metal. You are in the case of hydrogen embrittlement, hydrogen charging. This is a very specific case. Okay. So now, dissolution is quite easy to understand because we are releasing anions. This is what we call an anodic process. No problem. Now, what we have to think about what's happened about the reactions that are able to catch electrons. You have here a list of common reactions that can happen, and they are able to attract electrons to themselves. The first one is they are dissolved oxygen. So there is dissolved oxygen in solution, no problem. But according to the pH of the solution, so now we need to implement a new information, which is the pH of the solution. So the quantity of acid available in the solution, two reactions can take place. Two different reactions can take place. The first one is this one. In acidic solution, if dissolved oxygen catch 4 electrons in presence of a lot of protons, you will create water. In the case of neutral solution, actually, this is not water that you will create. You will create hydroxide, OH-, which is kind of interesting element. Normally, we should see it later. Okay. In solution, you can also have some metallic ions. If conditions are reached, these metallic ions can catch also electrons, and you will create a metal. Of course, sulfate, nitric acid, and so on. So you can see there is a lot of choice in the number of cathodic reactions, so reactions that are able to catch electrons, according to the environment in which you will be. So to have this exchange of electrons, we have to look about the thermodynamic. Here, this is a small example, but it's very helpful. What we have is in corrosion, we are not using the Gibbs free energy, but we are using the potential. And what we are doing is we just compare potential between the cathodic reaction which is catching electrons, and reactions that are releasing electrons, anodic reaction. And if, for example, in this case, we are looking on the dissolution of iron in acidic environment. It was mostly my first example. So if you look on that, you look on the thermodynamical data, you will see that you have a cell, because you are doing a difference of potential, and it is 0 + 4. This is positive, the value is not negligible, so the reaction can happen. Okay? So that means that if we have to have an idea about if the reaction can take place, we need to have tables. Here, there is two examples of tables. The first one is mostly the same as the second one. The idea is just to have some very positive reaction and negative reaction. Okay. They are standard potential. That's our rule to compare reactions. And here, this graph is more important. It's kind of distribution of potential of mostly all metallic materials. So because it's very small, here it's graphite, platinum, and zinc. Okay. So if you look and you think about the previous small equation that I gave, if I can mix platinum, for example, with zinc, so if I just look on the difference of potential, I know it will be quite high, almost 1.2 volt. That means that a reaction will take place. So usually if you think about zinc and graphite, okay, graphite may not be destroyed, but zinc may dissolve. I will illustrate a bit like this, or I will, okay. So that means that I can have a look on materials in solution, applying this kind of electrochemical potential chart. So I have a first example, a simple one, a very funny one actually, for corrosionists. I mean. Okay, I have a brass that I would like to immerse either in sulfuric acid solution or nitric acid solution. So if I ask the question, that means that it will have a difference. Okay, so that means that I have a metal in the environment. First, have a look on the environment. What is the environment? Okay, sulfuric acid, nitric acid, both are acid. That means there is H+. And because they are strong acid, that means that H+ may react more rapidly than the dissolved oxygen. Okay, that's the first point. Dissolved oxygen is quite heavy in solution, so oxygen takes time to move in the solution. It's a mass transport limitation. Hydrogen is very small, goes very fast. Think about hydrogen, embrittlement, and so on. It's a way to remember. Okay, so I have first treated the case of H+ in my two chemicals. Now I have to look on the other anions, which is anions. In the first one, I have sulfate. And in the other one, I have nitrate. If I look on thermodynamic and potential data, I will see that sulfate are quite stable in solution in water, which is not the case of nitrate. Nitrate, we can find a reaction. And for example, this can be this reaction. The nitrate in acidic solution, they can produce a gas and produce water. So that means that in one solution, I will have some troubles with the anions, sorry. And O-3 will play a role in the reaction. Let's see what's up. Now we have two elements in a brass. So just because brass is a mixture of zinc and copper, so that means that it could have two reactions. The first one could be the reaction of electrodissolution of copper. The second, the reaction of zinc. Okay. As we have no time, I was searching in the potential scale. So I just give the potential. The highest potential is for this element, and the lower potential is for zinc. Here you have the ranking of potential. To help you, I will use a scale, and I put the potential along the scale. So here they are the most highest potential, the lowest potential. So maybe, probably you already use this, but it's important to remember. This is the gamma rule. Actually, to know which kind of reaction will take place in corrosion, we are just drawing a gamma. So to draw a gamma, first we write all the electrochemical couples that can exist, and we underline the elements that we have in solution. Okay, that's the element that I put in red, actually, copper, H+, Zn. Now to write a gamma, up, left, down, right, down, left, up, right. Okay, so this is like that. If the reaction can take place, that means that this cross, I have the two elements. So in my solution, what I have H+, I have zinc. That means like H+ can react with zinc, giving Zn2+ and providing H+. Okay. Can I do exactly the same with copper? To do it with copper, I should have copper 2+ in solution, H2+, sorry, in solution, and the reaction should provide H+ and copper, which is not the case because in my solution, I have copper, metallic copper, and H+. So I cannot draw this gamma. Only this part of the reaction will take place. Zinc will dissolve in acidic solution. I will produce anions I will produce cations zinc and H2. Okay? So now if I'm inserting in the nitrite ions in my scale bar, so I know that I have minus NO3 minus in solution. So now I have all this in red. What kind of reaction I can have? I still have the first one. I'm allowed to write it. But now I have another one. These ions can play with copper. And you could also say, yeah, but these ions could play also with zinc. Okay? So I have three kinds of reactions that can take place at the same time. What they are saying, this reaction? At the end, they are saying that zinc dissolve, but also copper dissolve. Okay? So if I try to summarize, at the beginning, I had some mixture between copper and zinc. If I put this solution in, I inverse. If I put this solution in only sulfuric acid solution, I will only dissolve zinc. Okay, no problem. And you will see, if you look the surface, you will say, yeah, but there is a lot of grains appearing and crystals appearing. Yes, actually, there is a second process. If you remove zinc in a brass, copper are not anymore attached to the lattice, so they tend to rearrange, and you can have such kind of beautiful crystals. At the opposite, if we are in nitric acid environment, we said that both elements will dissolve. So let's have a look. Here, this is the boundary of the cell. So that means here I have a small leakage, but let's focus here. That means that we should have holes in the metals which appear here. Actually, both elements are dissolving, zinc and copper, and they are not dissolving at the same kinetic. So all the surface is dissolving, which is summarized here, but the copper resists a little bit more than zinc. So that's why you have something like very disturbed surface. C'est ça. I'm trying to remember the time because I forgot to. Ça va faire une heure. Okay. Okay. So you see that the environment will play a role because it can destabilize metals and components in metals. Remember this morning my story about manganese sulfur inclusion? It's almost the same. So, and after there is a lot of kind of cells that can happen. Cells means one electrochemical reaction, another one electrochemical reaction. A first cell is materials. They are not monocrystals. I said it this morning. So that means they have grain orientation. And because of grain orientation, you don't have the same atoms on the surface. So you don't have the same energy. So some surface can become more reactive than the other one. This is what we call a dissimilar electrode cell. For example, this is the case here. One grains will dissolve, whereas the other one will not dissolve. I already illustrate this one. It was my rod bar deep in water. I said it will have some dissolution deeper than the air-water solution because of oxygen gradients. This is a concentration cell. Okay, I have a gradient of oxygen. Where the oxygen can be consumed, the reaction will be oxygen plus electrons. But where there is no more oxygen, the only reaction that can take place is dissolution. And you have exactly the same in the drop, I already said. You can also have salt concentration. This also works. This is a practical work that you are using often, and maybe you already done this during your studies. But here it's because you have a different concentration in sulfate, so you have a gradient of potential between the two electrons. I said that temperature before is also a key parameter. Actually, everything is driven by the Arrhenius law. This is an exponential law with temperature and gives activation energy of reaction. This is a typical example of what's happened. Here we have a compressor station. We have hot gas going to a pipe, and because the pipe is either under the sea or in a soil, there is a gradient of temperature in the pipe. Actually, in some point, so here it's increased because you have a elbow, but in some point, when the at a specific point of the temperature, one part of the metal will dissolve, the other one will remain stable. That's here, for example, the reaction. And we call that thermogalvanic corrosion. Okay. So now, from a thermodynamical viewpoint, how can I have an idea about the resistance of my material in an environment? So in a high temperature environment, we are using the Ellingham diagram. I will not talk about them. I will talk about other diagrams, which are called Courbet diagram or potential pH diagram. This diagram have been drawn by Courbet and his team early 90s. And actually, the idea was to predict stability, not only of metal, but also of oxide. And the second idea was to predict this stability in water. So the first point is water totally stable if we change the potential of the solution and if we change the pH? So there is some equation, I will not go there, which is important to keep in mind is actually Courbet diagram. This is kind of potential scale, pH scale, on which you will have always two parallel lines, which are defining the stability domain of water molecules. Below this line, you will associate H plus of water and create H2. In the above line, you will degrade water molecules. So that means here, water is not stable. Here, the water is stable. Okay? So on this diagram of stability of water, we can also stick or paste the diagram of stability of any kind of element. Let's have a look on what's happened for iron. So there is a lot of equation dealing with where an iron oxide, where iron is stable. I will just give you the schematic of that. This line is an horizontal line. That means that the reaction that takes place involves only the element, is ions, and electrons. And this boundary defines iron, metallic ions, to ionic ions, iron, sorry, so Fe2+. Okay? And you have another one, which is here, iron 2+ can become iron 3+. The vertical line, actually, they are not anymore electrochemical reaction, they are chemical reaction. For example, this one. So what is the meaning of this one? Here, I just have iron 2 plus, iron 3 plus, sorry. But if I had OH minus, remember, one of the reaction of dissolved oxygen is to produce OH minus. So I can have some OH minus in solution. They can attract because one is positive, one is negative, and they can generate hydroxide, sorry. Okay? And when the equation actually is more complicated because you need to involve electrons, iron, oxygen in the reaction, you will have these oblique lines. There is, so like that you can define, according to the two lines of the water stability, what we will find. For example, at this potential, at this pH, if I put iron rod in solution, I should not have any more iron, but I should produce iron oxide. Okay? If I'm increasing pH, I should produce iron ions. Okay? These lines, they can move actually because of concentration in solution. That's the reason why there is two graphs. So here, with the scale that I choose, is not so easy to observe. When you will have the slide, it's slightly better. And also, sometimes it can change also the form of the elements that can appear. Okay. Ooh. Okay, sorry. So we just see that concentration play a role, but also temperature. If I'm trying to produce the same graphs when I'm changing the temperature, I will have different boundaries. So let's look on this boundary, for example. If you compare to this boundary, so the temperature is quite high. Here it's 25 degrees, 100 degrees, 200 degrees, and 300 degrees. You can see that changing the temperature, that's mostly why this graph exists, is changing the temperature, I'm changing the area of each domain. Okay, so I'm changing the stability properties of species that I'm developing. So for who is interesting in corrosion, that means that this graph can help to define at least 3 domains. The first one is the immunity. Immunity means that a metal will remain exactly as metallic. So passivation means that the metal will interact with the solution, with its environment. An oxide layer will be created, and the dissolution of the metal should be strongly limited. Last domain, which is corrosion. In this domain, no oxide layer can be produced. Nothing is stable. The only solution that has the system is to dissolve. So here, for example, you have the chromium, copper, aluminium, nickel. So you can see that there is, for all of them, different diagram shape. Okay? That means that if you want to predict the stability of an element, you have to look on the element itself. You cannot transfer knowledge from one to another one. Okay? I said that gold is very stable in water. Let's just check. So water stability is here. So you can see that according to the Prof diagram, to become unstable, you should have to strongly increase the potential. So you are here to an over potential where the water molecule start to be cracked. And it's easier to crack water molecules than to have oxide. It's easier to have to crack water molecules than to create hydroxide gold in the standard condition. At the opposite, if you look on magnesium, so stability domain of magnesium is here. Magnesium starts to dissolve here, so it is quite difficult in water to get magnesium, pure magnesium. You can have magnesium with oxide, but pure magnesium, metallic magnesium, will never exist in water. That's the thermodynamic aspect. However, as I already said, that this diagram has only thermodynamic and they are not taking account any on the kinetic of the process. So this is the insert here actually. If you change the quantity of oxygen in a solution for if you change the quantity of oxygen according to the pH of the solution, the corrosion rate of the material will change. Okay, that means that you have a lot of factors to think about in corrosion. So usually it makes you crazy at the end. So that means that we have mostly no problem to understand what will be the stability of a material in environment, but our main problem is to define the corrosion rate of the element. So aluminium in water should corrode. You should not have any aluminium in water. However, there is. It's because the corrosion rate, so the tendency to dissolve, is very low. So we need experimental techniques to assess the corrosion rate. So there is, let's say here, two direct and indirect methods. The first are the direct method. Some of them are intrusive technique. We are doing physical techniques, so mass measurement, electrical resistance, visual observation. We can use also electrochemical techniques. I said that electrons are moving, so we can count the electrons that are moving. And there is also non-intrusive technique, because when the materials are in structures, intrusive techniques are not very useful. So we will have eddy current, ultrasound, acoustic emission. So there is a panel of techniques that we can apply. So here, just to give you an idea, we were comparing in a previous joint research between France and Japan the result of corrosion rate of a steel immersed in an acidic solution, and we were using NDT technique. At the end of the experiment, we have done what we are doing always, weight mass measurement. And because we want to increase the corrosion rate, we were using electrochemical measurement. So in these techniques, we were forcing the dissolution of the material. If we force the dissolution of the material, we know the electrons that are given to the pumping, to the material. So we can estimate the rate of the corrosion. This is in blue. And you can see that along the experiment, we have seen always a difference between the non-destructive technique and the electrochemical measurement. Who is right? Actually, at the end, we just observe what's happened and we make some weight measurement. So weight measurement is always giving the truth. And you can see that electrochemical measurement, they are quite far from the two other techniques. There is a reason for that. It's because electrochemical measurements, that means that we count electrons. There is electrons that are dissolved, but some electrons are also used for other things, for other second, reaction that are not playing a role in the material degradation. So that's the first point. For some techniques, here, this one, it gives some differences. So that was the direct measurement. So now, what are the indirect measurement techniques? If we want to follow and if we want to know if there is any corrosion, the first point, as I already said a lot, there is hydrogen. So we can form hydrogen. So we are doing hydrogen monitoring. If the material dissolves, that means that the potential, this energy, is changing. So I can monitor the corrosion potential. If I'm dissolving materials, I'm changing the chemical properties of the solution. I'm putting some ions in solution, metallic ions, so I can follow, for example, the water chemistry using conductivity, resistivity, pH, if I'm consuming too much the H+. And also, when there is a corrosion, that means that the system equilibrium is changing, so I can have fluctuation in the fluid, in the pressure, in the temperature. So that can be online, that can be offline, sorry. We can follow exactly the same. With the offline technique, which is interesting, is we can also insert some spectroscopic measurement to follow better the quantity of very low concentration of some species. This is, for example, instrumentation of online and offline technique of a high pressure, high temperature loop that we have in France. Okay. So how can I monitor the corrosion rate? First is to, if I assuming that all electrons are playing a role in the corrosion, I will monitor the number of electrons. And for that, I will use the Faraday law. I will calculate the quantity of electrons per time. And I will be able to convert it in dissolution rate. So I'm going quite fast on this one. The most important is I will be able to have conversion data from the quantity of electrons per unit of surface that have been corroded, and to give a quantity of material loss, an equivalent, which is easier to understand for engineer. Okay, so here you have kind of chart of conversion between milliamps per centimeter square versus what you could have per millimeter of material loss per year, for example. Okay, you are able to do this. What you are doing with the results. The first point is for a specific attack, which is the uniform general corrosion. You remember this morning I gave this this picture. So there is some helpful values, and they are this one. If you lose 0.1 millimeters per year of your metals, it is said that you have a good corrosion resistance. There are very roughly idea about the corrosion rate. Between this value and 1.5, it can be acceptable according to the environment you are using. That means also, if you are selecting this material with this corrosion rate, you have to think maybe to oversize the system. And what we are saying is often if the corrosion rate is higher than 1.5 millimeter per year, it's not satisfactory. Okay, so corrosion rate depends about the temperature, because the temperature changes the concentration of dissolved oxygen. Okay, if I have less dissolved oxygen, so I will expect to have a different corrosion rate. They are here, for example. If I'm consuming oxygen, I will change the corrosion rate. Another point is, if I'm providing sufficient chemicals to react, I can also increase the corrosion rate. So for example, here it's the flow velocity of a solution arriving on a metal. And if I'm looking only on the flow velocity, I can see that higher the flow, higher the corrosion rate. And also, if we mostly goes to the atmospheric corrosion, the thin layer of water that can weight the material, it can also affect the corrosion rate. Okay, so maybe I will go a little bit faster now. If I'm focusing on electrochemical tests, there is one reason to focus on that. It's because this is tests that you can implement in laboratory. They can give a very fast information. Sometimes very easy to interpret, sometimes very difficult. So electrochemical test, you need what? You need to quantify the electrons. You will be able to have idea about currents, and you will be able to have idea about potential. When you have all this information, you will be able to have your corrosion rate. That's for engineer, and for the scientist, you want to understand the mechanism of corrosion that happens. For that, you will use a 3 electrode cell. Here you have a very old model of electrode cell, but it's worked pretty well. It's called a 3 electrode cell. You need to have an anode. So anode is very easy, the metal that you want to characterize. You need to have a cathode. Cathode is an inert material on which you will force the consumption of electrons. Actually, you want to have the cathodic reaction on it. And a setup which is called potentiostat. And the potentiostat, actually, what you are doing is you apply a potential to the metal. The metal will either try to release electrons. Instead of releasing electrons and react directly, you take the electrons, you count them, and you give back the electrons to the second electrode. And to close the system, you need to have an electrolyte. So electrolyte will be a fluid, a moist soil. Actually, the electrolyte should be either a model electrolyte because you want to characterize your system in a very controlled environment, or the reality of the environment. One tricky point with this is as we are using a reference electrode to apply potential to materials, we have to select one reference electrode. So the most important, the first one was standard hydrogen electrode. So for that, you need to have a hydrogen bubbling in a small capillary with a wire of platinum. It's not so easy to handle with dihydrogen gas, so there is some other standard electrodes. They all have their own potential. Their potential is stable in time, no problem. But they have all a difference in potential with the standard electrode that we are using as a real reference. So there is always a shift. So this is important also. If you are looking on papers in the literature, don't take directly their value, but have a look on the values that they have, correct from the potential that you are reading, and usually you should convert it in the international scale, which is the standard hydrogen scale. And like that, you will be able to compare all the data that you get. Okay, so what can I measure? First, the potential of the material. Okay, so I'm measuring the potential. The potential is the fact that the metal try to adjust the potential difference between the solution and itself, and it has to create a new interface. There is two evolutions. The first one is the potential increase. So Corrosion said, that's good because something happens on the surface of your metal and it becomes more stable. And if the potential decreases, that means that that's not good. It's become active. Okay, that's the first description of the potential. I will not go to this one. It may be, with time, it will be a little bit tricky. Okay, so here you have an example. For example, here that is 3 metals. Actually, this is a mixture of copper and nickel. So you have pure copper, you have pure nickel, and mixture of them. So here it's 30% of nickel in 75% of copper. And if you immerse them in a same solution, you will see there is a different evolution of potential. So nickel increase, that means nickel become protected by an oxide layer. At the opposite, pure copper is dissolving. And what's happened for the intermediate composition? If we still have a lot of nickel in the solution, we still have an increase of the potential with time. You see that it is different. That means that the chemical composition of the material have an effect on the growth of the oxide layer and its stability. And if there is not enough oxide, nickel, potential decrease. Okay. So the potential you can access to material evolution, and if you compare, to have some idea about what is the material. Okay, the second technique actually is, before I was not applying any potential, I was measuring the potential, but I'm also able to apply a potential. So if I applying a potential, I can also switch the potential with time. That we are drawing here. Actually, this is, you have two lines, two theoretical lines. The first one is the line of the current according to the potential if I'm looking for the reduction of H+. So H+ in solution catch electrons and becomes H2. So here there is almost no current. Here there is a lot of current related to this reaction. And at the opposite, if I'm scanning the potential in the other solution, I will increase the current related to the dissolution of iron. Okay, that's the two currents occurring at the same times for each reaction. Actually, what we have is the kind of compromise of these two curves. They are still here in a dashed line, and you will get such kind of evolution. Okay. So in this domain, the main reaction is H+ becomes H2. After this point, the main reaction, the main active reaction, and because of current, is the dissolution of the metal. So here, it's more for scientists. It's start to give you idea about potential stability of your material. Using this technique of potential scan, actually there is subdivision of techniques to try to access to the reaction rate. And the first one is a linear polarization. Actually, it's applying a small potential when you are close to the free potential of your material. This technique is also very important because I said that previously this slope was for the hydrogen, but hydrogen is not alone in the solution. So here, for example, is the slope for hydrogen without oxygen in solution. Now, if I have oxygen in solution, I will see that the slope will change a bit because there is a contribution of the oxygen reaction in the solution, and the oxygen needs to move. If I have less H plus in solution and more oxygen, what I will have is this kind of curve. Actually, here I can see in this curve that there is a large contribution of oxygen in the reaction. So oxygen contribute to the draw of these curves. So I know if there is a lot of oxygen or not in the solution, but it also contributes to the kinetic of the dissolution. For example, here I have almost no oxygen. The corrosion rate is quite low. If I'm increasing the oxygen concentration, the corrosion rate becomes higher. And you will find this for other parameters. For example, chloride. If I'm increasing the chloride concentration in solution, I will change the shape of the curve and the reactivity of the material will increase. If I'm increasing the temperature, I will also increase the quantity of electrons released by the metal. So the current will increase. If I'm changing, for example, the quantity of molybdenum in a passive material, I will also change this shape of curves and so on. Okay. So that means that this part of the curve, which we describe, is highly sensitive to the environment. I'm moving a little bit further for the next. Which is interesting is if I'm focusing only in the curve, which is related to the metal dissolution. I don't care what's happened in the opposite. I mean H2, H plus giving a H2. I have such kind of shape. For example, I have a large bump, and this large bump means I have a strong dissolution of the metal. Because I've put a lot of ions, metallic ions in solution, they react at the surface of the metal, and they create a blocking film. If I'm blocking the dissolution of the material, what's happened for the current? Decreasing. Okay, so here it's decreasing, here it's decreasing. I put the two charts because one is for US, the other one is for European. It's kind of gymnastic of reading. So here and here, the current is decreasing because I create something on the surface which is able to limit the dissolution of the metal. If it's for stainless steel, it will be a chromium oxide. The chromium oxide here will still decrease the current. Why? Because I'm filling the void in the oxide. An oxide layer is always porous at the beginning. But with its maturity, with time, I'm filling voids. So it's more dense. If it's more dense, metallic ions have more, it's more difficult for metallic ions to go through the oxide and to be released. However, when the potential becomes too high, the oxide layer cannot maintain its stability, so there is too much external force, and the currents start to be released. So the oxidation restart, the dissolution of the metal restart until there is nothing anymore that protects the material. Okay, this kind of curves can help you to understand the history of the material. And in any case, for example, if this material comes to this potential in your system, you know you are safe. The current is very low, perfect. But if the potential becomes here, for any case, galvanic coupling or something like that, here you know that it's become tricky and nothing will, metal will start to be degraded. Another technique from electrochemical measurement, I'm just only focusing on the three main techniques. There is a lot of has been developed, but these three techniques are the ones that you can find usually in literature. The last one is electrochemical impedance measurement. Usually, if you know what is electrical impedance technique, it's exactly the same, but in our case, we are in solution. Okay? So you choose a potential, you apply a fluctuation of potential, you record the fluctuation of current, and you love mathematics, and you draw what we call the Nyquist diagram or Bode diagram. Okay. First, from the Nyquist diagram, what you will see is different size of loop. This is the same four materials that I was using before: nickel, nickel copper, alloys. You can see that the loop is totally different. Here in the windows, the value of the impedance are very small. And please trust me, here you have the loop for the nickel. Here you have the nickel with the alloy with 70% of nickel. And here you have the other element, the other alloys, which contains more copper. So you can see that the loop strongly decreases. If the loop is decreasing, that means the corrosion resistance of the material is decreasing. Sounds correct. If you have the possibility, you will see before the graph of OCP, and we were saying that, okay, the OCP of the copper is decreasing. Okay. And what? And here we are copying what it is done in electrical impedance measurement. You know exactly what kind of electrical circuit you are studying. So that means for us, this reaction can be simulated by electrical circuit. Why not? An oxide is a capacitor, more or less a real capacitor. It is a capacitor. An electrolyte, it's ions. It's an electrical resistance. In oxide, I can have also electrical resistance because there is defect. So water can go to the defect. So you see there is some similitude between electrical impedance measurement and electrochemical impedance measurement. So that means that we can find some electrical equivalent circuit, and the word equivalent is quite important, trying to fit what's happened. So for example, for these four diagrams, we were choosing these three electrical circuits. I can explain very fast. The first element here, which is common for all, is the electrolyte resistance. The Q here is, roughly speaking, the oxide resistance, or the surface capacity, sorry. And here, this is the electron transfer resistance as a surface. Okay? And you can see here, there is what we call the Warburg. Warburg means that the systems becomes under the influence of mass transport of something. So that means that there is a mass transport of an species, an active species, in the system. And when you have this, that means that you have another contribution of reaction. electrical double layer, and space charge. It's quite a little bit more complicated as an equivalence system, but it's totally online with the fact that the nature of the surface and the oxide are totally changing. Okay. What is tricky with this technique is, if you look for a stainless steel, you can find in the literature at least 10 models. And they try to fit, and they are all fitting very well the experimental value. Which one is the right one? That's always the question. So in my French lab, there is some researchers that are discussing about this, because the first point is you should always have the easiest electrical circuit. Either you increase the number of parameters, you are sure to fit. But is this electrical circuit as a reality? For example, this one is quite funny. This one means that you have two systems, one after the other one. Kind of painting. Is an oxide layer a paint? Not sure. Because an oxide layer is defect, so all the systems should react at the same time. So there is a lot of discussion, and this slide is mostly to say, okay, I can fit, but what is the reality of the fit that I choose? For that, we have a lot of techniques to understand, so we will use spectroscopic techniques. We are implementing each day new techniques to have an idea about what's happened for the oxide layer. So that's the regular technique. I said that scientists, as scientists, we like to develop new technique, new approach to better understand what's happened during corrosion process. All the techniques that we have done previously, or we have used and see previously, they were applied on macroscopic scale. I mean, usually this is samples of 1 centimeter square, and you immerse it. But you would like to see if each grain has its own reactivity. We have seen that in the cell definition. So for that, you need to play with another techniques, which are local electrochemical measurement. Here you have a scheme of taken from the literature, for example, where actually they were studying polycrystalline of copper. What they have done first is they make a BSD map, and actually they are trying to correlate the reactivity of each grain according to the grain orientation. So here, this is a grain orientation. Here, this is a reactivity map. So some grains with a particular orientation are more reactive than the other one. The other solution is also to understand why sometimes local corrosion occurs at the interface of two phases. This is an austenite ferrite stainless steel. So you know that there is a stress gradient at the interface about the two phases. You really want to see if there is an effect of the stress gradient at the interface. So you are using local electrochemical measurement. You generate pits, and you have a map of reactivity, saying that if the step of gradients is too high, you will generate dissolution. Okay. So right now, we just have seen materials, environment, and just before, Sylvain was giving a talk about mechanics, and he was saying, okay, but mechanics also degrade materials. Yeah. So what kind of relation we can find? And there is actually a lot of works dealing with, at the same time, mechanical and environmental load to characterize materials. And there is a phenomenon, what it is called synergy. That means that the degradation rate of a pure chemical or pure mechanical loading is totally modified by the interaction between these two parameters. For the next and last talk, I will give an example normally. Okay. Okay, so thanks a lot for your attention.